Well, good morning. I'm Jay Shin, NASA's Associate Administrator for Aeronautics. I'm not reading this script because I don't remember my name, but I was given such a good script, so I'm trying to stick to it. Welcome to today's another exciting ARMD technical seminar. Today we have Karen Heminger from Langley, who will talk about electron beam freeform fabrication. I actually like that EBFÂ³. That graphic looks marvelous. It reminds me like Indiana Jones movie trailer. But we'll have a very interesting, exciting presentation today. The electronic beam freeform fabrication process was developed by researchers at Langley as a replacement for forgings. This manufacturing process offers significant reductions in cost and lead time. I have a lot more to say here, but I don't want to steal thunder from Karen. And furthermore, I'm not the technical expert in this area, so I should let Karen talk about this. Karen is Associate Principal Investigator for Materials and Structures in one of our project, that is a subsonic fixed wing project of a fundamental research program. For the last 7 years, she has led development of the electronic beam freeform fabrication technology for high-performance, low-cost fabrication of metallic structures for aircraft, launch vehicles, and spacecraft. So truly aerospace applications that you will hear about today. She was recognized for her work in 2007 when she received the NASA Exceptional Achievement Medal. She has authored or co-authored one patent, more than 25 formal publications, and made 75 presentations on this subject. And so she's well recognized and respected in the community. She and I actually spent time together at Virginia Tech. We, of course, didn't know each other, but in the same years. She graduated from Virginia Tech in 1989 from the Materials Engineering Department, and she has also received her Master of Science degree in Materials Science and Engineering from Virginia Tech in 1999. And she has been working since 1986 at Langley, studying as co-op student. So with that, Karen, thanks for coming here, and please come up, and we're excited to hear from your presentation.
Thank you, Jay, for the kind introduction and for the opportunity to be here today to talk to you about the electron beam freeform fabrication process. Throughout the talk, I'll be referring to it as EBF3 because it's a little bit shorter. I'm starting off with a slide to talk about all of the team members that have been involved. This has truly been a team effort, and without them, I wouldn't be here, and the process would not be what it is today. So I would like to start off with an acknowledgement of all the folks that have back at Langley that have been working very closely with me over the past several years. Next slide, please. This is an outline for my talk today. I'll start off with the inception of the technology, and then talk a bit about characterization of the materials that are produced using the EBF3 process. I'll then proceed on to some of the technical challenges that we've come across with the process, and specifically looking at what needs to be solved in order to reach full commercialization. And then I'll switch gears a little bit and talk about applications, both current applications and some potential future applications that we're working on, both for aeronautics and for space vehicles. And then I'll end up with a little bit of the possibilities that this technology may offer for in-space support. Next slide, please. So starting off with the motivation, a little bit of the process description of the EBF³ process, and then the benefits to talk about the technology inception. Next slide. Next. Okay, so in structural metals used in aircraft today, typically you see aluminum or aluminum lithium used in fuselage and in wing panels. The highly loaded areas of the aircraft, like wing tips or wing roots, and some of the hot structures in the engine are use the titanium alloys. High-strength steels are used for landing gear, and Inconel can be used in the hottest sections of the engine. So there's a large amount of metals that go into today's aircraft. And even with the future aircraft moving towards composite structures, there's still a significant metallic component in aircraft structures. And so it's an area that we wanted to look very closely at to see if what is new on the horizon. We've been building airplanes out of metals for a long time. What's new on the horizon? Next slide, please. So our motivation, we were challenged back around 2001 to come up with what is new in metals. And specifically looking at efficient lightweight structures, it has to be a cost-effective process, and potential for enabling new alloys that are beyond the current conventional suite of materials that we use were three of the areas that we wanted to look at. And what we ended up with, we didn't set out to develop a disruptive technology, but we ended up with a disruptive technology. And by disruptive, I mean that this is a technology that has the possibility of replacing a segment of the manufacturing market as it currently exists today. Next slide. So back in 2001, when we first started looking at what's new in metals processing, layer-additive or deposition processes had been around for several years, but they were primarily using lasers, either a CO2 or a neodymium YAG laser. And the problem with lasers trying to do metals fabrication is that lasers are reflected off of shiny surfaces, and metals are inherently shiny. In addition to the coupling efficiency between the laser and the metal to be able to melt, there are also issues with the energy efficiency. Only 5 to 10% of the energy, and this has improved over time, but in 2001, only 5 to 10% of the energy that was actually pulled from the wall ended up being used to create the beam. The rest was all waste heat. So looking at the energy efficiency, the other issue was the feedstock efficiency. A lot of the laser technologies use powder feedstock, and depending on the size of the molten pool they were working with, you could either get 5 to 85% of the powder captured in the molten pool. The rest ended up just being waste powder. And what really prevented laser deposition technologies from taking off in the commercialized world is the fact that they were limited in the deposition rates. They could only get up to, at the most, 9 pounds per hour, but most of them were down in the half a pound per hour. It's just not an economically feasible or viable technology. So when we were looking at metal deposition, we said, deposition, to be able to put the metal where you need it and only where you need it, is a good concept. Let's look at what other things could we use. And so we chose to work with the electron beam. Electron beams have very, very good coupling efficiency with all electrically conductive materials, such as metals. They've got very high energy efficiency. Working in a vacuum gives you a nice clean process environment. And we work with a wire feed because of the vacuum. We're working with a solid feedstock in the form of wire, but 100% of that wire is captured into the part that you're building. And we've demonstrated deposition rates on the order of 30 pounds per hour. So we believe that the electron beam process has commercialization potential, and it solved many of the problems that existed with the state-of-the-art in 2001. Next slide, please. So the core technology for EBF³ is that it's a rapid metal fabrication process. It's layer additive. It does not require molds or tooling, and so a large expense that's used for building tooling for forgings and that does not have to be absorbed when you're using an EBF³ process. The properties that we've observed are equivalent to rot properties, and I've got some charts later on to show you about that. And we've so far demonstrated this on aluminum, titanium, nickel, and iron-based alloys, which are all of the alloys of interest that I showed on the earlier slide for aircraft structures. Next slide, please. So the EBF³ process, we start with a CAD drawing for the part that you want to build. That part is sliced, the CAD drawing is sliced and fed into the EBF³ equipment. The E-beam is then turned on to create a molten pool, and wire is fed into the molten pool, and then the part is translated in a layer-by-layer basis to build the parts up. We've been teased about building a replicator in the vernacular of Star Trek. Next slide, please. The system that we started off with in 2002, we're still using this for most of our process development for our large fabrication experiments. And this system is an electron beam welder that we purchased, and we had it modified, adding a double wire feed so that we could build the layers up. It's got a high power electron beam gun. We're only using about a third of the power that is available to us, but because it was a commercial off-the-shelf system, we bought something that could suit what we needed. The vacuum chamber is a 7 by 9 by 9 foot steel chamber, and the build envelope is on the order of 2 by 4 by 5 feet inside of that vacuum chamber. Next slide, please. Several years after that, we started looking at trying to build a smaller system. The process is exactly the same, so the physics of the process is still using the electron beam to build up a part. But we've scaled everything back so that we could do some demonstrations for 0G. And so we built a 3-foot cube chamber with a build envelope about the size of a shoebox. And we've got a 3 kilowatt gun for safety on the aircraft and just to scale everything back. It's enough power for what we need to do. Next slide, please. So this is, let me set up for you, next I'm going to have a video, but let me set that up for you. This is a picture looking in the chamber of our large electron beam freeform fabrication system back at Langley. If you roll the video, please. This is looking through the door, just showing some of the motions capable in the system itself. Here we're closing the door, and then we'll evacuate the chamber down to about 10 to the minus 5 torr. Now our first layer is beam only, so the beam is coming down from the top center of the screen. And the first layer is just to clean off the oxides on the surface and to give us a nice warm surface to be able to adhere the deposit to. Now we're showing the subsequent layers being added on. This is all 2219 aluminum, and this is real time. We can build faster than this, but we're using 0.63-inch diameter wire, and this is the only part of this that is molten is the shiny part of the molten pool of the image there. So the process solidifies rapidly. So some of the reasons I've already talked a little bit about the EBF³ process, but the main idea is that we can build near-net shaped parts, so you can minimize scrap, reduce the part count. It also offers efficiency in design, lighter weight designs, and enhanced performance. The unitized components, unitized I mean being able to build things in a single piece. So instead of building an assembly that needs to be riveted or bolted together, you can build components of some complexity into a single part. And that offers the opportunity to, because this is a layer-additive process, we can integrate different functions into the structure, or we can change the material on the fly so that you've got different alloys at different points. If you have reason to need different alloys with different properties, we can tailor the properties locally. And finally, it's got some green manufacturing ramifications. Again, this was something that we hadn't set out to do, but it ends up being a nice benefit in that we're minimizing the waste products and its energy and feed feedstock efficient. Next slide, please. To give you an idea as to what I mean by energy efficiency. Starting from titanium ore, these are all of the process steps that would be required to go from titanium ore to a final product. On the left, in blue, is the conventional processing that we would use today. So you start with the titanium ore and go through about 12 different steps before you get to the final part. There are losses in energy and in titanium itself along each one of these steps in the process, because you have to forge a billet and then you skim cut it and you press it down, skim cut it, roll it, skim cut it again. So you've got a lot of losses in the process of just going from titanium ore to a billet and then machining it out to a final product. The DARPA has been working on a new process and has funded several organizations to look at low-cost titanium. And the low-cost titanium process basically skips steps 1 through 9 to go directly to a powder form. And so you've dropped out a lot of the work that goes into building the preform. And then what we're doing is, we can take that powder, go directly into a wire form, and then that wire becomes the feedstock for E-beam freeform fabrication. So we've, in using this future set of processing steps, you can eliminate about half of the steps and a lot of the losses in both energy and in titanium. Next slide, please. This shows you in a little bit more detail of the kinds of savings that we're talking about. And this is the reason that industry is so excited and is really investing heavily now in trying to get this technology commercialized. Along the top line is a conventional machining, and these are real numbers. This is really the way it is done today to build structures for aircraft parts. It'll start with a 3,000-pound billet of material. Machine it down to a 150-pound part. There are a lot of, obviously you're losing a lot of the titanium. There's a lot of energy that goes into making all of the chips. And furthermore, there's all the cutting fluids that are required to keep the part cool during all of that machining operation. And those cutting fluids have to be handled as hazardous waste at the conclusion of the process. So instead, what we're proposing is you would start with a rolled sheet or plate that would become part of the process, or part of your final part, and then use the wire feedstock with the EBFÂ³ process to put the material where you need it. There's a little bit of final machining, but it's just taking it to your final tolerances. And you end up with the exact same part at the end of the day with a lot less titanium lost and less cutting fluid to have to try to dispose of afterwards. Next slide, please. Now I'm going to change gears, talk a little bit about the characterization of some of the materials that we have produced using EBFÂ³ process, specifically looking at the microstructure's mechanical properties and some of the structural integrity. And I'll try to go easy on those of you that don't have a material science background out there. Next slide, please. On the left, the picture that you see, this is what a typical plate microstructure would look like. And so today, the aircraft that are flying would have the kind of microstructure that's shown on the left. And it's kind of an equiax grain structure, so everything is kind of circular in shape. And if it's rolled plate, sometimes you'll see some of those grains that really stretch out. In comparison, on the right is the type of microstructure we're seeing with the EBFÂ³ process. This is more what you might see in a casting. You see the fine grains and the large. There's a variation in the grain size, but it's still a relatively small grain structure. Next slide, please. Now, taking the picture that was on the previous chart on the right and looking at it higher magnification, that's now shown on the left. And what you see is things that look kind of like a fern structure, little fingers. Those we would call dendrites, and that is a natural occurring, that naturally occurs in castings, on cooling. When you take a molten metal and cool it down, that naturally occurs. But we have relatively small grains in the as fabricated microstructure. Now, if we go through a T6 heat treatment, this would be a standard heat treatment that would be used for for increasing the strength of rolled plate in that in conventional materials. We end up transforming the grain structure, so the grain boundaries are retained, but we've erased, if you will, that finger microstructure. So our microstructure doesn't end up looking too much differently from a forged type microstructure. It's a little bit different, but not too much different. Next slide, please. So what does that mean for the mechanical properties of this material? 2219, part of the reason that we've chosen this alloy is it's aluminum 6% copper alloy. It's very easily weldable, and it's readily available. It's used in the space station. It's not used as much in aircraft structures today. There are higher strength alloys that are used today. But we have also done deposition with other real conventional aircraft alloys. So the 2219 is the alloy that I'm showing you, but we have done extensive testing on a variety of other alloys as well. What this chart shows you, on the vertical axis on the left is the tensile strength, so the first two sets of bars, the yield strength and the ultimate strength mapped to the left, and then on the right is the elongation, so that third set of bars is the elongation. And the blue bars are the EBFÂ³ plus the T6 heat treatment, as I showed you in the microstructure on the previous chart. And then the gray bars are handbook typical values for the same heat treatment. And what you see is that the properties are really quite comparable. I don't have error bars shown on the chart here, but the error bars are within 1 or 2 KSI. So it's a fairly tight data range that we have in the EBFÂ³ parts that have been fabricated. So this gives us some confidence that although the microstructure may look a little bit different, mechanical properties are still performing as you would expect in a conventional material. We're still doing a little bit of work to understand what that microstructural difference may mean in other mechanical properties like fatigue and fracture toughness, but we've got some confidence that this will work. Next slide, please. One of the other things that we have looked at is functionally graded aluminum. And here the base plate is 2219, again, that aluminum, 6% copper, and we've graded it up to 100% pure aluminum at the top. So this is what you're looking at on the picture on the left is a cross-section of a 10-layer build. And so the first layer was 100% 2219, and then each layer was a 10% change in the chemistry, building it up to 100% of the pure aluminum. And what we see here is the microstructure on the bottom of the 100% 2219 is about what we have seen in the other EBFÂ³ deposited 2219. 100% pure aluminum doesn't have it doesn't have alloying additions, and so it doesn't have a lot of features. Again, that's what you would expect. And grading up through the middle, what you do see is that we have a continuous gradation, even though this was deposited in a stepwise fashion. Next slide, please. Looking now at the hardness, it's hard to do a tensile property when your material is changing continuously, but looking at the hardness will give us a feel for what the properties are in that. And so on the chart on the left is the data from the hardness data. It's a hardness trace going up the center of the microstructure on the previous chart that I showed to you. And so the axis, the zero axis, is the plane of the base plate. So everything below the axis is in the base plate itself, the forged material. And then everything above that line is in the deposit. I've got two graphs here. The one on the left is the 2219 to pure aluminum, or 1100 aluminum. The one on the right is 2219 to 2195. 2195 is an aluminum lithium alloy. And so just showing that we've done gradation with both of them, and it's gone from 0 to 100%. What you see in the data is that, again, you see a nice gradual, the pure aluminum is softer by nature, and then you see a gradual shift from the 2219 to the from the hardness in the 2219 to the hardness in the pure aluminum. Next slide, please. Shifting gears a little bit, looking at the Ti-6-4. Again, this is one of the alloys that's very heavily used in both commercial and military aircraft. This picture shows on the left a cross-section of a single bead deposit. Looking at the picture on the right on the bottom shows you what your typical plate microstructure would look like. And you see kind of a similar microstructure to what we saw in the aluminum. You see a the white dots is an alpha phase, and then the center parts are the beta phase on the lower microstructure. The top microstructure is showing how different the solidified microstructure is in the Ti-6-4 deposit area. And you see what we would call a Wiedemann-Statten alpha-beta lath structure. But again, heat treatment will bring that structure down to something that looks similar to what we have down below. Next slide, please. Looking at the Ti-6-4 tensile data, again, properties, just like we saw with the 2219, the properties are quite comparable between the as deposited and the annealed wrought product. Next slide, please. So the next thing that we wanted to do is, if we're going to incorporate this into structures, we wanted to understand what the structural performance might be. And so we built three sets of panels, machined. All of them had the same final geometry. And these panels are in the order of 24 inches long and 8 inches wide, with a single blade stiffener down the middle that's about 3/4 of an inch high. The machined, we started with 1 inch thick plate and machined it down, just leaving the blade stiffener integral to the base plate. The riveted, we started with 1/4 inch thick base plate and then used an L bracket and riveted it on to give us the blade stiffener. And then we E-beam freeform fabrication deposited a stiffener on the third one and machined it so that all three of them had similar widths or similar thicknesses of the stiffener. Next slide, please. And this is the compression buckling test. It was tested in uniaxial compression. And what we noticed is that the machine panels performed the best. On the chart, you see load on the vertical axis versus displacement. And so the machine panels performed about 5% better than the EBF3 panels. The riveted panels are a little bit stiffer because of that extra material. But the riveted and the EBF3 panels gave us comparable max load capacity. One of the things that we've noticed in the EBF3, and I'll talk about it a bit later, is that we do have some distortion that occurs because of the focused heat source. And the distortion in going back and doing finite element analysis to compare to the mechanical, the physical compression data, we were able to explain that the reduction from the machined to the EBF3 is because of the shape change in the panel that occurred due to the distortion during the EBF3 process. So if we can get a handle on the distortion, we believe that we can increase the structural capacity of that EBF3 panel. Next slide, please. Now to talk a little bit about technical challenges, and specifically looking at what else needs to be figured out before we can take this to commercialization. I'll talk briefly about preferential vaporization, process control, and residual stress. Next slide, please. Next slide. Thank you. So the first one, preferential, what I mean by preferential vaporization, we've got a molten pool in a vacuum. And so if you've got Ti-6-4, you've got titanium, aluminum, and vanadium sitting in that melt pool. Because you don't have an atmosphere to suppress vaporization, you tend to get, we tend to have a little bit of metal vapor that comes out of the molten pool. The aluminum, we lose aluminum at a faster rate than we lose the vanadium or the titanium because the aluminum has a lower melting temperature than the titanium or the vanadium. So the picture on the right is the same types of microstructures that I've been showing in the past, only it's now laying on its side. So the base plate is on the far left of that microstructure, and then you see the deposit off to the right. And then the two lines below it, you see a titanium trace and an aluminum trace. This is just looking at the chemistry along the center line of that deposit. The vanadium didn't change, but the aluminum, you see about a 1% drop. So we start with 6.5% aluminum in the wire and the base plate. As soon as you've melted anything, whether it's in the wire or the base plate, as soon as you get melting, you see the drop, that step function drop in the aluminum content because we've melted in a vacuum. It's a function of temperature and pressure, but it's an issue for process repeatability. So this is one area that we're looking closely at how do you mitigate this, or how do you at least understand it and make sure that it's repeatable so that when we are trying to use this technology in a production environment, we're able to get the same part every single time you build it. And the real challenge is, you see the red line at the bottom of the aluminum trace. If you dip below that red line, you are no longer within the Ti-6-4 chemistry bound. And that means your properties are going to drop off, and that you're going to have problems with you're not going to be able to certify the process. Next slide, please. The need for process control is shown in this chart. One of the things, the chart in the middle shows the shape of the melt pool. And so the black line, the smallest melt pool is the shape of the melt pool on the first layer of the deposit. And then each line out is layers 2, 3, 4, and 5. And so what we see is the melt pool changes with temperature. Your first layer is going down onto a cold plate, and it freezes out fairly quickly. It's got a nice tight melt pool. The next time we put a layer down, everything's a little bit warmer, and so the melt pool starts to stretch out. If you don't make any changes to your process, or if you're not watching the process, you don't have the same size, shape, or temperature in the melt pool, and that's going to have ramifications for the chemistry and the distortion, residual stress, and everything else that we see. Next slide, please. So we've put cameras, thermal imaging cameras, into our system. The picture on the left is the top view looking straight down. So you can see the white line is the trace of our beam itself. The orange is where the metal is molten, and the blue is where it's solid. And you see the funny little step out on the far left of that image. That's where the wire is entering the melt pool. The picture on the side is giving us a side view. So again, the wire is on the left, and you can see where that wire is being melted in the beam, and then the melt pool traces out from there. And we understand that we need to look at both the height, so that we build the part that we have programmed to build, and the top view, so that we can control the temperature. Next slide, please. Localized heat, we understand, and this is nothing new. This has been very commonly known for decades in the welding industry. But localized heat induces distortion and residual stress. You tend to get very high compressive residual stresses right at the root of the deposit, or of the part where you're trying to weld it on. And it just is trying to pull that deposit off of the base plate. Next slide. So this is a series of finite element modeling experiments that we've run, and we've been comparing finite element to the experiment to try to help guide what experiments and how do we mitigate the residual stresses and the distortion that's developing in the material. Across the bottom you see the base plate, and what you see on the far right is the stress state with one bead. The next one over shows 3-layer height, what the stress rate. So we're looking at how the stress state changes as the layers are built up. The blues are high compressive residual stresses, and then the pinks are the tensile residual stresses, counterbalancing that. But what we do see is that after about 3 to 5 layers, the stress state really doesn't change. And so we know that in order to, if we're going to build an integrated structure where the deposit is part of the base plate and it's going to stay that way, if we want to avoid any distortion, or we want to minimize the distortion and residual stress, that we need to do it in the first couple of layers of build. Next slide, please. Looking then at how does the part move when those residual stresses are relaxed, when you unclamp it. What we're showing here is the vertical displacement. The cent on the far right of the slide is the deposit. And what we see is that the base plate doesn't actually curve. It bends right in that area of high stresses, right underneath the deposit. And the experiment that we were running here was we had a series of different clamping distances away from that deposit. And so what you see is that the distortion is less when you clamped it and constrained it up closer to the deposit. The further away you get, the further the clamping gets away from the deposit, the more the deposit is allowed to, the base plate is allowed to move a little bit while the process is cooling down. Next slide, please. We've been working very closely with Boeing, Lockheed, Spirit Aerosystems, and the Air Force, and we've recently formed an alliance with these companies. It's a joint funded alliance, but what we're trying to do is develop some process standards and to catalyze growth of a supply web and to address all of the technical challenges that I've just described. NASA has been asked to lead this because of our leadership and the fact that we've been on the forefront of this technology development for so long, and also because we offer the potential for providing public benefit without private preference. And what I mean by that is that we'll develop this for the good of the nation, not for the good of one single company. But this group has just started working together, and we've been exchanging ideas in that. But the real idea is we want to try to pull together the buying power. Boeing, Lockheed, and Spirit each had activities on their own, and so now in working together we can get a much richer database in a faster time frame with all of us working together. The other thing that allows us to do is catalyze growth of a supply web. Right now there are no companies out there that use the EBF³ process for profit. So if Lockheed or if somebody decided that they wanted to buy a part built with EBF³, there are not places that they could go to buy parts currently in the marketplace. And so there's a growth that needs to happen, and having all of us working together, we can show that there's a much larger volume of need as compared to any one of us trying to go out and convince a company that, yeah, this is a good technology to invest in. Next slide, please. All right, I'm going to talk now about some applications. So I'm done with all the materials stuff, big sigh. I'm going to talk first about current applications, and the first place where this is going to really see use is replacing existing parts. And so I'm going to talk a little bit about how we may be replacing existing parts, and then some industries outside of the aerospace industry that we've talked to that has interest. Next slide, please. So the way engine casings are built, they start with a 3-inch thick forging. They machine down to a 1/2-inch wall thickness, but they have to have a 3-inch flange at the top, which dictates the size of the forging. So what they would like to do is start instead with a 1/2-inch thick forging and then add bits of material on to build up the bosses and flanges and that they need for the final part. It reduces the buy to fly ratio and the billet sizes and all the good things that we talked about earlier. But adding details onto forgings is really the first place that this is going to see real commercial benefit because of the cost and the reduction in the amount of material that you need. Next slide, please. A concept for cryo tanks that we've been working on is instead of buying a big thick piece of, there's a theme here, you can tell. Instead of buying a big thick piece of aluminum and machining it down to leave an orthogrid stiffened structure inside, we've been working with companies that can build a very large, the picture on the top is a 14-foot diameter cylinder. It's a single piece. But they can't put stiffeners on the inside of that because of the shear forming process that's used to build it. And so what we're proposing is there a way that we could get inside after it's been shear formed and be able to build those stiffeners in place? And this is where some of our crossover into our portable system starts coming in, because you've got to be able to get onto the inside of this cylinder. Our portable system could be put onto a robotic arm and moved around on the inside of that cylinder to build the stiffeners that you need. Next slide, please. The other idea is to be able to build more complex shapes. So instead of designing something that's in assembly, we design components that have some complexity and build it in one shot. And so this just shows a couple of different parts that we've built to date out of aluminum and titanium. And these parts range in size from 4 inches high to about 22 inches in height. So there's a variety of different things. But this allows you to get some complexity like internal hollow cavities that can't be machined unless you build it in multiple parts and assemble it or weld it together. Next slide. Some of the industries that we have talked to that have expressed interest, aerospace industry, obviously. The tool and die industry, for building the dies and the tooling themselves, because of the functional gradient, you can hard face a tool, a casting tool, and be able to get longer life out of that casting tool. The automotive industry, not for full production automobiles, but for aftermarket parts, or perhaps for the racing circuit and things like that. There's a high demand for customized parts, and so talking about the customized automotive industry. Medical implants, so that a hip joint can be designed directly for the patient instead of saying, okay, you look like a medium or a small. Be able to build a hip joint that fits the socket that it's going into. Sporting goods, and I think that's the first place we'll probably see Tiger Woods out there with the EBFÂ³ golf club. And finally, repairs in remote locations. If we can build a small system, and this harkens back to some of the work that we've got in the interest in space, is the ability to give the autonomy of being able to build whatever you need when you need it on demand. And there are some locations on Earth that may have that requirement as well. Next slide, please. So looking now into the future, everything that I've talked about so far is just replacing the way we build things today. If we can get into the designers' heads, how would things look in the future? So looking at some new unitized structures designs, functional graded structures, and some integrated systems. Next slide, please. So the idea on novel structural design, we want to be able to go from a straight stiffened design. So right now, an orthogrid panel would have straight stiffeners in an orthogonal array. And it's partially built that way because this has been designed to be assembled. And so instead of designing something with a straight grid structure like I'm showing here, we think you can optimize that structure to not only carry loads, but also perform other duties, and put a stiffener, allow the stiffeners to curve. Because we're putting the metal only where you need it, you can build something like this with the EBFÂ³ process. This is not easily built with other processes to date. And so the curvilinear stiffeners, they have potential benefits in damage tolerance, in acoustics, in reducing the weight further, and in enhancing other performance metrics. And so this is what we want aircraft structures to go to today, or to go to in the future. Next slide. One example of how this might be used is aeroelastic tailoring. Right now, a monocoque wing is built with ribs and stiffeners and spars that are all on an orthogonal array, and they're all riveted together. The new airplanes coming out, the structure looks exactly like that. It's just glued together with composite. But the challenge is, the problem is that's designed to carry the aero load, the aerodynamic loads, but the bending and the torsion that occurs in an aeroelastic in an event, things like wing flutter and that, are not taken into account. And so the thought is, can you build something that couples the bending and the torsion so that the wing naturally deflects when it's hit with a loading? And so being able to put curvilinear stiffeners, we believe we can change the structural design so that you can naturally get that kind of a motion into a wing and completely passive structure. Next slide, please. Designing for acoustics. Right now, again, with a straight stiffener, you get what you get acoustically, and they go through and they add acoustic liners and acoustic dampening material to try to shield the passengers inside the aircraft from the drone of the engines. If instead you could curve the stiffeners and tune the frequency of that panel so that it will naturally not resonate in the same frequency range as the engine is producing acoustic noise, you can not only reduce the acoustics that's going into the cabin, but you can also reduce the fatigue loading that is going into that structure because of the vibrations that are being built in. So just some possibilities, things that we're trying to work towards, and things that we think that this type of a technology may be able to apply. Next slide, please. Functional gradients. Right now, this is, I showed you some pictures earlier. Right now, this is a, gee whiz, this is something that we can do. We can build, we can do a gradient in either the plane of the deposit, which is shown in the top picture there. So it changes from 100% of alloy 1 to 100% of alloy 2 as you're laying down the deposit, and it's purely done with a double wire feed of changing the feed rates of the two wires that are being fed into the molten pool. Or we could do a build height gradient, which is the picture that I showed you earlier in the talk. This allows us to control locally the chemistry, the microstructure, the properties. We've got to think a little bit more as to how we may be able to use this, but I think that there are real potential. And so, I'm laying it out there as we now can build a single piece material, a single piece part that's got different materials with different properties at different locations in the part. How can we take advantage of that to really drive the performance of our structures? Next slide, please. Integrated systems. This is a riveted structure that's shown. But what you see in the red lines is these are areas that have been identified for selective reinforcement. And what I mean there is actually putting some ceramic fibers into the structure. Right now they're just doing it by adhesively bonding ceramic fibers onto the metal surface. And what that does is it serves as a crack stopper so that you get longer life out of your panels, and it locally stiffens the panels. So instead of using an adhesively bonded stiffener, can we find a way, and we've been working a little bit on this, can we find a way to selectively reinforce? So we incorporate those ceramic fibers into the part as we're depositing it. The other potential is the vehicle health monitoring world, where we want to be able to monitor what the vehicle is doing, both temperature and strains and stresses and cracks and everything else. And so the ability to embed sensors into the body of a single-piece metal structure, we think that there are ways that you can use this technology to be able to do something like that. So, may open new design space. Next slide, please. Okay, last section of the talk. Trying to look now, instead of in all of the aeronautics world, looking at space, supportability in space. And so I'm going to talk a little bit about why we might want to do something like this in space, and then show you the results of some zero-G flight testing that we've done. So I've got some fun video to show you of that, and talk just briefly about some possible applications that the technology may offer some benefits. Next slide, please. So the need for supportability. Long-duration missions, they've done a series of Monte Carlo simulations down at NASA JSC trying to predict what parts will fail so that they know what to throw in the toolbox to bring along with them on a mission to Mars. What they found in the simulations is that each time they ran the simulation, different parts broke. The good thing that they found, though, was that each time they ran the simulation, the volume of material, the mass of the material of the components that broke was roughly the same. So we've got some confidence that if you could send up the material that you need and build on demand the parts as they fail, then you've got a more robust mission, and you've minimized your resupply from Earth and are able to fabricate or repair the parts that you need. And if you happen to get up there and lose something or come up with something that you may want to build that you hadn't planned on building or hadn't planned on bringing with you, you've got the opportunity to do that too. So it gives you some additional flexibility in the mission. And I know when we've talked to the astronauts, they're all drooling. So next slide, please. So we started, obviously, a 100,000-pound system with a vacuum chamber of 7 by 9 by 9 feet is not going anywhere. The portable system that I've showed you pictures of, that's about 1,800 pounds. Again, it's way too big, way too heavy to go to the moon. But it was built as a demonstration so that we could do the zero-G flight testing. Now, if you're going to the moon, the reason that we have the big vacuum chamber is because we need to keep the atmosphere out. when we're going to the moon, the atmosphere is already what we need, so let's take advantage of that. You can reduce the weight significantly. You can drop the weight by half just by eliminating the vacuum chamber and support structure associated with the vacuum chamber and the pumping. And so if you can go to something that works outside of the spacecraft, now you've got the potential to just bring a small positioning system like a little robotic arm, an electron beam gun, and some wire, and you're good. And so we think that we've got some concepts on the board, and we think that less than 100 pounds is a doable system. Next slide, please. Now, one of the things that we had to understand and we were told, well, if you take this in 0G, you're just going to build ball bearings. And so we wanted to look closely at, how is the process going to change as we reduce the gravity? First thing we wanted to look at is the cooling path, because we know that the cooling path influences the temperature. First layer, just like in the residual stresses, first layer down is going onto a cold substrate, and so there's plenty of thermal mass to cool that bead down. As you build up in layers, not only do you have a lot of retained heat because you're building onto something hot, but you've also reduced the cooling path to down through the part that you've built. And the reason that this is an issue, next slide please, is because surface tension is a function of temperature. And our question was, the two droplets here, before we did our 0G flight test, this is a little bit exaggerated, but those two droplets have equivalent droplet volume. And so the question was, is the gravity working with the wetting forces to spread out that molten pool, or is the surface tension really driving the process, and so that's pulling that bead up into a tight bead? Next slide, please. So we've done a series of 5 weeks of flight testing down at NASA JSC on their C9 reduced gravity flight. And for those of you that aren't familiar with that aircraft, they get on the order of 15 to 20 seconds of 0G. You can get a little bit longer if they're flying a lunar or a Martian parabola, followed by a 1.8 G pullout. And they do about 40 cycles per flight. And so what we did was we only deposited during the reduced gravity portions of the flight. Since everything solidifies as soon as we turn off the beam, we were fairly certain that we weren't changing anything during the pullouts. Next slide, please. Okay, so next I've got a series of videos that just shows you some of our results. And before we run those videos, I just want to set up what you're going to be seeing. The beam is coming down, as in the previous set of charts. The beam will be coming down from the top, and what you see there is the wire feed nozzle. Right now it's got a little ball of aluminum that came from a previous deposit sitting on the end of it. And in this case, we're just moving the base plate, and we're looking through a little camera through the port. So run video, please. The first pass, again, is just that preheating pass. When the wire starts coming out there, it shoots that bead off. And you see that the wire goes down, the wetting forces overcome the surface tension, and we are able to deposit quite well. We started a little higher than we should have been, which caused that bead to form at the beginning. This is that same circle now about 8 layers up, and you can see that we're able to, it looks just like on Earth. We did have the opportunity to learn from the 0G flights. We had a couple of situations, and it's shown in these next 2 video clips, is we had the height off. And so as long as you're feeding the wire and the wire is melting close enough to the molten pool, close enough to the surface, everything adheres. But you'll see in the last video coming up that if you get your height off, things go bad in a hurry. And so you can see when we start separating from the molten pool, it just builds a bigger and bigger blob until we get close enough. What's encouraging about this is that the wetting forces do overcome the surface tension, so the process does work. The other thing that we've learned is that height is absolutely critical, especially in a reduced gravity environment. Height is absolutely critical. And I have here the part that we were building in that video just to show it to you in a little bit more detail so you can get a feel for the size of those features. In 0G, those blobs, because they continue to build up on the end of that nozzle, the blobs are much bigger than you would get in a 1G drip. So this is the part that went down, and it looks pretty good, but you can see how much when the drips started getting away from us, how much of a surface change that we had there. So where could we use this? We think that this could be a concept for supporting long-duration human exploration missions, either on the moon or on Mars. Next slide, please. We've also looked at the possibility of being able to use this for on-orbit assembly or repair, being able to build extremely large structures in space. And we had worked with DARPA a little bit. DARPA actually funded us to do our very first set of zero-G flights because DARPA was interested in building a 100-meter space telescope in geosynchronous orbit. And it was just not in one of the things that they wanted to demonstrate was that you could manufacture it in orbit, that you didn't just send it up and try to do the assembly. There was actually a manufacturing process, a component to that. And so it's possible that you could use this in conjunction with pre-manufactured parts for doing some on orbit assembly or repair. Next slide, please. The other thing is that just like the need for autonomy on the moon, there are similar places where self-supportability is required on Earth. Down at the South Pole, they are without resupply for 6 months out of the year because of the ice flows. The Army has interest in reducing their supply chain, and they've actually deployed a machining center. They're bringing bar stock and machining components in Kuwait, in Baghdad, to be able to fix Humvees and things like that as they go. Navy ships and submarines also have some interest and some need for having the autonomy and the on-demand repair and fabrication that the EBFÂ3 process may offer. Next slide, please. So in summary, the EBFÂ3 technology has really been led by NASA Langley since its inception around the 2002 timeframe. It does have some elements of being a disruptive technology. As we've talked to industry, they've been very excited. They say, we want to replace our forging with plate that we build up the stiffeners on it because we see the possibility here. And we see the real potential in saving weight and being able to build parts much faster. Right now, to get those 3,000-pound forgings, they're waiting 18 months. So if you can build something in 6 weeks, you've saved them an awful lot of time and money. It cross-cuts from aeronautics into space, as both areas that NASA is interested in, but it also has cross-cutting ramifications into the manufacturing section at large. I think that to me, the thing that's most exciting is what's spinning off is some of the new structural designs. It may be that EBFÂ3 is not the way some of these new structural designs end up coming into play 20 or 50 years from now. But EBFÂ3 has given the designers the vision of something that may be possible. And so I think that it's kind of cool for me to see that it's expanding and the influence there. And we've demonstrated in zero-G for use in space. Next slide, please. This is my last slide, and it just shows you the timeline from inception. First system delivered, the ground-based system, in 2002. And it just shows you we've come a long way in a relatively short period of time. We are hoping that we see the first EBFÂ3 parts certified and flying on aircraft in the 2011 timeframe. And we're excited about the potential for being used in structures for a long time to come. So I thank you all for your attention, and we've got some time for questions.
Thank you, Karen. That was a fascinating briefing. I'm Beth Dickey with NASA Headquarters Public Affairs, and I'll be moderating the question and answer session this afternoon. Do we have any questions here at Headquarters? Dr. Alonso.
I'll ask one. Hi, Karen. Very nice briefing. You yourself alluded to the fact that the mechanical properties appear to be very similar, but that there are issues with fracture toughness and maybe fatigue, some other things. Can you expand on what we know and what we don't know about that yet?
We've done a little bit of fracture toughness and fatigue testing. Lockheed and Boeing have done a lot more than we have at NASA, actually. And they've done enough testing to have confidence in the materials and the properties that are being produced in those materials to be going ahead with commercialization. I think that heat treatment is probably going to end up being the key. They're already heat treating parts of engine case size and larger anyway. One of the advantages having an electron beam, we can change the character of the beam, and one of the things we're looking at is, can we change the heat treatment on the fly? So build the part and then heat treat it in situ, so you don't have to go through the additional step to be able to influence that. So it is an area that we are looking at. We haven't seen any showstoppers so far, but it does need some more in-depth study.
All right, thank you. We've got some questions that have been emailed to us. Here's one for you. What materials have you fabricated using EBF³?
We've used, I've shown you a lot of data on the 2219 and the Ti-64. That's been the workhorse alloys that we've done. But we at NASA Langley, we have done 2000 series, 4000, 2000, 5000, 6000, and 7000 series aluminum alloys. And what that means for those of you that don't know aluminum alloy chemistries is that we've covered the whole gambit from high strength materials to high stiffness and high toughness alloys that are used in different locations in airframe. And so we have looked at different alloys with different success. Some of the alloys we have real problems with losing some of the alloying additions, and so we've got a concentrated effort looking at the chemistry and trying to understand how we can control the chemistry. We've done work with Inconel 718, which is commonly used in the high temperature sections of engines. We've done a little bit of work with ferrous-based alloys, and I know that the companies out there have also done some work with some of the some tungsten and some of the heavier metals, things that aren't in the aerospace world. But in the aerospace world, we've looked at most of the alloys that we would currently use today and try to figure out how we can either use something similar or make some modifications to those alloys to be able to make them. And that's where the new alloy component of the work. It may be that we end up with an EBF³ alloy. There are casting alloys, there are forging alloys, so maybe in the future we'll have an EBF³ alloy in particular.
And what are the limitations on the sizes of the parts that you can build with this process?
Right now, the limitations, because we're working in a vacuum environment, the limitations for the size of the parts we can build is really a function of the size of the vacuum chamber that you have, the size of the positioning that you have. Right now, we're actually looking at at NASA, we've looked at very fine detail, trying to put down some intricate components. Industry has really been interested in, let's just put the metal down there, we'll machine it to final shape. So they're willing to live with something that, a bead that's the size of my thumb, and then just machine down to whatever thickness they need. We've been trying to drive the wall thickness down to maybe 1/10 of an inch or smaller so that we can get some intricacy and maybe build some internal structure so that you've got an internal component with some complexity on the inside that you can't get to.
Before I call for questions at our field centers, let's see if there's anything else here at headquarters. Here we go, right here.
Can you talk about the limitations of the gradient or the steepness that you can vary your vertical profile?
Are you talking about a chemistry gradient? You're talking about a geometric gradient?
The geometric gradient.
A geometric gradient, right now, if we're just building straight on top of each other, we can build about a 40 to 50 degree angle. However, we do have gun tilt capabilities and table tilt capabilities, and the fact that we can deposit in 0G gives us confidence that we can build. You can weld to the side, you can weld upside down, you can weld against against gravity. And so as long as you keep your molten pool small enough that gravity doesn't overtake you, the limitations in the geometries that you can build are more going to be what can you program and how can you access the parts. We could actually build, if we were building a wind tunnel model, we could build a fuselage and then just bring our gun 90 degrees to the fuselage and build that wing right on the side. And so we could do an overhang. So it's more of a fixturing and accessibility and programming issue.
Do we have another question here at headquarters? Here's another email question for you. What sort of modeling have you done to support the experimental process development research on this?
Modeling is an important part because we can model things and test out different scenarios before we try to go to the trouble of being able to do them experimentally. And we have done thermal-based modeling to understand the residual stresses, and I showed you some of that in the presentation. We've also done some modeling of the melt pool itself in looking at the process control so that we can understand how we can control our processing parameters and be able to feed that back into the system to maintain the process throughout the build.
One more. Composite structures are rapidly replacing metals on new aircraft. What's the future of metals in emerging all-composite aircraft?
Great question, Beth. The composites, Boeing's 787 Dreamliner, they advertise as an all-composite vehicle. It's still 40% metals. And so it's that's partially a public face that's being put on. But there are the heavily loaded, what's changing in aircraft structures and where we see the transition from metals to composites is in the skins and the frames and that. So the highly loaded members like the bulkheads, the wing root areas, and all of the engine components are still going to be metallic. The engine components, especially when you get into hot section, you can't get away from the metallics because of the thermal capacity of the metals. And so even in an all-composite aircraft, there's a significant amount of metals, and the technology is versatile enough to allow us to work with a variety of different alloys for a number of different applications.
All right, we're not hearing any questions from our field centers anymore here at headquarters.
That was a nice talk, Karen. You said you can put ceramic fibers inside the stuff. How do you do that?
Well, our first trials, we melted the ceramic. But we've got some tricks that we're trying where we can shield. The problem with a ceramic fiber is that the electron beam, when it hits it, it'll charge, and so the beam gets deflected into other places. And because it'll charge, it'll sit there and kind of stall. And we actually took some beautiful alumina fibers, aluminum oxide fibers, and turned them into a nice molten puddle because we sat too long on them. And so what we're working on right now is some different techniques where we can focus the electron beam into the conductive parts of the structure. And be able to place the ceramic fibers or something perhaps like a fiber optic, be able to place something like that underneath. So we've got some tricks that we're trying to develop. It's going to take more work. And that's the exciting thing is that once we've now gotten past a lot of the basic process development, we're ready to commercialize this. And where we want to go next, we want to continue to have EBFÂ³ as an element of the materials research at NASA Langley. But where we're going next is we're going to use it as a tool for being able to build integrated structures exactly like what you're talking about, or be able to use it as a tool to build some of these new structural configurations like we've thought about.
Oh, you fed right into our next email question about the process. Once it's been commercialized, what do you see NASA's role in the technology development as being?
I think that NASA we've been recognized as the leader. Industry is very interested in working with us because of that recognition, and it's been a real honor to be able to work with so many different people within industry with this technology. But I think that our goal is to be able to truly hand it off to industry so that there are companies out there that are doing the research. We don't want to keep all the research in-house because I think it'll stifle the technology. It's ready to be born and to get out there. And so the technology, what we want to do is hand it off to industry, allow universities to play with it. It's a rich field. There's a lot of potential. And where we're going to be going is using this as a tool to do things that NASA needs. We won't do everything that everybody needs, but we want to do what NASA needs to be able to build next generation aircraft and space structures.
And I'm really interested in what excites you most about doing this. Is it riding the Vomit Comet, or is it something else?
Riding the Vomit Comet was a great experience. That was a lot of fun, and people accused us of making up the experiment to be allowed to fly on the Vomit Comet. That's not true. The experiment really did go first. I've had a great team to work with. It's been really a lot of fun and a lot of energy around coming up with something new. We started this with a CNI. CNI is the Creativity and Innovation Program at NASA Langley. It's a director discretionary funding at NASA Langley. So we started with a little bit of money with CNI, a little bit of money out of aeronautics, and have been able to grow it to what you see behind me today. So we've been able to grow it into a huge field. And it's really been gratifying to see something that I've worked on actually get to fly on an airplane, and something get out there in the commercial world. Because we started it as just an idea and have built it and built the partnerships and the team to be able to take it out there. And so I think that the whole birthing process, taking it from an idea into reality, getting it out there, and then the group of people that I've had the opportunity to work with to be able to make that happen has just been very rewarding for me personally.
And we do have one question from Langley Research Center. Langley, go ahead.
Okay, my name is Sobieski. I am from your home base at Langley, and I have the question about what makes the basic physical difference between the use of electron beam and the traditional welding technology of depositing metal by means of heating it with gas torch or electric arc?
Did you catch that?
We didn't catch all of that. Are you asking the difference between conventional welding technology and EBFÂ³? Yes, that was it.
Yes. Okay. EBFÂ3 came out of the welding world, and it does have a lot of the same problems. It shares a lot of the same challenges, and frankly, that's of good news to us because that means we can rely on the welding world and all of the answers that they already have to be able to help point us in the direction. The real difference here is that instead of building 1 or 2 or 3 layers up, we're building up the entire structure. And so now instead of welding 2 pieces together where you have a little bit of weld metal, you've actually got a major part of the component has been added on layer by layer instead of just taking 2 pieces and welding them together. Does that answer your question?
Yes, thank you. That does. Thank you. Well, we'll call it a briefing now. Thank you very much for your presentation. Thanks, everyone, for joining us here at headquarters and around the centers. You can learn more about this topic and other activities of NASA's Aeronautics Research Mission Directorate by going to the NASA website, www.aeronautics.nasa.gov. Thank you very much for joining us.